Swayam Prabha. Digital India. Educated India.
Good evening, everyone. Today we will try to actually do some demos on accelerating deployments. Okay, and as I showed you yesterday some videos, maybe today we will show you the demonstration by again connecting a webcam. There's some issue with the team viewer, but we will anyway show you some more videos today in case that does not materialize, right? Because it is getting struck. The team viewer video is getting struck. So no issues for that. But let us start with certain things wherein we'll try to show you the maximum demo stuff. Okay. So yeah. So yesterday, actually, we ended up at this point, right? That how do you actually deploy a model with TensorRT? Okay, and we showed you this particular concept. We showed you a demo, and we actually discussed this yesterday that we have either a TensorFlow or a Cafe or any other framework which basically is written using Python. Okay, and then you have a model importer which actually imports, okay, using a TensorRT, right? So the idea is you basically come up with a model which is a universal framework format, or at present you can use ONNX as well, right? So I've got two options of actually converting your actual model which you have trained it on a server, right? And then convert it into something which runs on an inferencing edge device, right? So you can use UFF or you can use ONNX. So we will show you ONNX also, and we have done it using UFF also, right? So let us see how we can show you both of this, right? So the basic idea, what we discussed yesterday was, you have a trained neural network model, you import that model, and then try to use a TensorRT optimizer, right, for trying to optimize it so that it runs on your edge device, right? So for that reason, you actually have this process which is internally done, right? You have to serialize it, then you generate 1 or 3 optimized plans, and then you get a plan file, right, which actually schedules, okay, for the kernel to execute whatever it is to be executed. So you take this optimized plan, okay, and then as shown, you basically create a TensorRT engine object, and then you run it using a TensorRT runtime engine, and that is how you basically try to deploy it on the edge device. So basically, you are trying to deploy the runtime. So this is the overall model which we discussed yesterday, right? So now today, we'll try to understand that when we are trying to work with TensorRT, TensorRT supports the following layer types. What does it mean? It means if you are using convolution layers, if you are using activation layers which involve ReLU, tanh, sigmoid, and you have this pooling max and average stuff, element wise sum product or max of 2 tensors, okay, and then LRN, then fully connected with or without bias, softmax, deconvolution. All of these layers could be converted from TensorFlow or PyTorch to a TensorRT survey, right? This is what it means. And now that effectively means that whenever you are trying to convert, okay, any model for inferencing, the steps would be like something like this. you actually convert, for example, if you are trying to do a image segmentation application development, so you convert the pre-trained image segmentation PyTorch model, or for that matter, a TensorFlow model, into ONNX or or UFF, anything, and then you import the ONNX model into TensorRT model. Okay, this conversion needs to be done, and then you basically apply certain more optimization, generate an engine. So technically speaking, once your model gets converted into a TensorRT runtime, okay, you can actually do the inferencing on that particular edge device, right? So we have written it on the GPU, so you can do it on the GPU, you can do it on edge device, you can do it on Jetson, any of these, right? So this is how basically it is done. Okay, so there are various ways of doing it. One of the ways what we are trying to tell you is this. Okay, you can actually see in literature and various other places, there are various ways of doing it. One of the ways is you either convert your TensorFlow program into a TensorRT program through UFF, or through ONNX. So this is the basic idea. Okay, so you have got various components in TensorRT. You have a ONNX parser, which basically converts. Okay, or you have a UFF parser. You basically take any trained model into the ONNX format as input, and you get a network object in TensorRT. This is possible. Okay, and then you take a network in TensorRT and you generate an engine that is optimized for the target platform. So this target platform can be anything. So ultimately, you basically take a network in TensorRT and generate an engine. Similarly, your engine takes an input data, performs inferences, and then emits the inferencing output. And logger basically tries to give you warnings, capture errors, and how you run and everything, right? So this basically is various component of a TensorRT. Now, TensorRT powered NVIDIA edge devices. Actually, if you see their benchmarking performances, they are quite good. Right? They are very, very good. So you can accelerate every model across the data center and add in computer vision applications, speech to text, NLP, for example, BERT, and various recommender systems, right? So all of this could actually be done, okay, on the edge devices using TensorRT optimizations, right? So it supports all major frameworks. TensorRT is integrated with PyTorch, TensorFlow, and you can achieve 6x faster inferencing with one line of code. So this is the basic idea. You can actually integrate everything. Okay. Okay. So TensorRT thing from TensorFlow. So now the idea is, let us say we have a TensorFlow program, and this TensorFlow program needs to be converted into a TensorRT program or a TRT program. So TF-TRT is what we generally call. So TensorFlow integration with TensorRT. Okay. So when you do this, you basically are trying to work with subgraphs. Okay, and then trying to understand how TensorFlow, okay, graph can be converted into an optimized TensorRT graph. So the effective idea here is your TensorRT is going to generate a model, a parsed model, and then it applies optimizations to the portions of the graph wherever possible. So we'll show you various graphs, right, in the next few seconds or minutes, rather, right? So we'll show you how basically a saved model, a TensorFlow graph, is converted into an optimized graph, right? That also you can visualize. So technically speaking, TensorFlow RT speeds up your inferencing by 8x for a ResNet 50 benchmarks, right? So there are certain things wherein you can see about graph optimizations. Okay, do not change the underlying computations in the graph. So that's very, very important. See, your computations won't change, okay, but the graph will be optimized. So basically you are restructuring the graph to perform the operation much faster and more efficiently, right? So this is the basic gist of it, of why do you do actually this, and how is that it's going to speed up. Okay, that is also what you are going to actually see. Okay, so now when you integrate the TensorFlow with TensorRT, okay, so TensorRT basically optimizes the largest subgraph possible in the TensorFlow graph, and if there is more compute in the subgraph, obviously the TensorFlow optimizes it more. Okay, so more computations are there in your model, right? More optimization you can expect out of TensorRT. So most of the graphs which are to be optimized and replaced, okay, with the fewest number of tensor node RT, so you generate a tensor RT node actually. So the idea is you can optimize and replace, okay, with certain specific less number of nodes as compared to your actual nodes in the graph, right? So that is what actually you are going to be doing, right? Now, this is how it actually happens. You create and train an ML model, or you get a pre-trained ML model. Both are possible, right? You save that model. Obviously, you are training your model and then you are saving your model. Once you save that model, you get a TensorFlow saved model. Okay, there is something which is called as TensorFlow frozen model. Okay, now this TensorFlow frozen model cannot be edited or it cannot be changed. That is what it means in for a layman, right? You can actually train a saved model again and again, but once you freeze that model, right, it has got all the weights, parameters, everything frozen, right? So you cannot actually use it for training again. That's what it means, and that is what you are going to optimize. Okay, so you're going to optimize that, okay, saved model from the frozen model, and then you deploy it with either a Triton server or you do it with TensorFlow. So now this is what I told you, that your actual thing of understanding at the first level of complexity is this, that you convert your TensorFlow program into a TensorRT optimized program, right? By converting it intermediately to a UFF or ONNX, right? So Open Neural Network Exchange format. Okay, so something like that. So this is what it means, that you're converting your TensorFlow program to a TensorRT program, right? Okay. So the idea is that you create a saved model or a frozen graph out of a trained TensorFlow model and give that to the Python API of TF-TRT, which is going to return TensorRT optimized model, replaces each supported subgraph with a TensorRT optimized code or a TRT engine operation, producing a new TensorFlow graph. So this is how you actually convert, okay, and use the saved model format, and this is how you get a frozen graph format. So if you see here, okay, this basic thing, okay, TensorRT import TRT convert as TRT, and then you are using a converter. You are just trying to actually save a saved model, okay, and then you actually get a frozen graph by using a converter convert, okay, function, and then you get a frozen graph. Okay, so this is how basically you would be using it in your program. Okay, this is just the idea of how you are basically using various converters which are available, okay, for converting your various models into various formats like a saved model format or frozen graph format. Okay. Okay. So one of the things when you want to work with TF-TRT is that you need to install TF-TRT. You have NVIDIA containers, as we told you in our previous sessions, as to how do you pull a NGC Docker container. So you pull an NGC Docker container and you actually use, okay, a tensor RT enabled TensorFlow thing, right? So TF-TRT container, okay, and this basically is supposed to be pulled or installed, okay, from a TF-TRT container, okay, from the NGC cloud. Okay, so what are the various parameters when you try to actually use this? Okay, so the parameters which can be passed, okay, so this is a command line interface option. Saved model CLI to TRT graph converter, you can work with any precision mode. Okay, so the precision mode which you can use is FP32, FP16 or FP8. What is the minimum segment size? So that basically means the minimum number of TensorFlow nodes required for a tensor RT subgraph to be valid. Okay, this when you go on practicing and running your programs, you'll try to understand, okay, all of these particular parameters. But just to have the completeness of trying to link, okay, how these parameters are actually connected, we are just trying to give you a very brief idea to this. Okay, and then you can use calibration, because calibration is needed. Yesterday I told you that when you're converting from FP32 to FP16, okay, it is done. But when you convert something from FP32 to FP16 to something like int 8, right, there is a calibration required, right? So if the precision mode is int 8, the calibration is needed. So effectively a calibration graph will be created. Okay, so this is what it means. Okay, and then you have the maximum batch size and the maximum cached engine thing, right? So the limit of the number of RT engines which can be cached per TRT engine operation, because it depends on the memory of your edge device, right? Based on that, how much you can cache is going to actually make your system slower and it can get stuck or something of that sort might happen. So that is why you are going to use some of these parameters. Okay, so let us try to do some benchmarking. Okay, so let us try to understand the inferencing portion on just CPU, CUDA, and TensorRT. So this particular thing is a very simple example of trying to import, okay, a pre-trained neural network model. So we are just trying to load an example image, okay, for the prediction, which you are able to see. Okay, now what we are trying to show here is this is an image, okay, and then there is some transform which is happening. So we are trying to pre-process this image, okay, and then we are trying to actually set a benchmark size to this example image. Okay, so you can do it using CPU, you can do it using GPU, and you can do it using TensorFlow RT. Okay, so we will get the prediction and probability for each class, right? So this is what actually is a very simple thing of where you are going to actually link it with the ImageNet classes, right? That is what you are trying to do. Okay, so yeah, so we'll run this and we'll extract the 5 top probabilities. This is for that particular thing. So it has detected that it is basically an Egyptian cat, it's a tabby, tiger cat, Siamese cat, and carton, right? So with these many prediction percentages, right? So now we will try to understand the speed test with the ResNet 50, okay, example. So what we are trying to do is, this is basically a TRT program, okay, and then we are trying to just show you, okay, that how basically for each of this, okay, how much iterations it's taking, how much time it's taking, with conditions of whether the device is a CPU, whether the device is using CUDA, and what when it basically tries to develop a TensorRT model. So this is just a very preliminary benchmarking thing which will help you to appreciate the optimized stuff, right? So that is what we are trying to do now. So here, so if you run this, okay, which we have just now run, it basically gives you 645.74 milliseconds, right? The average batch time. And we are running it for CUDA here, which is executing, which is telling you that it is giving you 91.85 milliseconds. So the idea here is, you are trying to run the same model on a CPU, which gives you 645.45 milliseconds, 645.74 milliseconds, whereas on CUDA, okay, the same model gives you 91.85 milliseconds for actually training, right? Now, TensorRT model, if you see, will take a bit of time. Yeah. So if you see this, it takes about 70.33 milliseconds, right? So the idea is from 91.85 milliseconds to 70.33 milliseconds, right? So this is basically like a very good what to say, reduction in time, optimized time, okay, because it's a very simple example, nothing we have done too much, okay. And if you see the prediction, right, it gives you almost the same prediction, right? 37% Egyptian cat, almost the same, everything is same, right? So if you see here, it's 37, 19, 11, 4 and 3, the same thing we get. Okay, so yesterday we were talking of, even if it is reduced prediction, reduced precision, right? You get almost the same thing, right? There's nothing much of a difference here, right? So this is what we thought we'll show you first, and then now once we have done this, the benchmarking demo, let us try to understand, right, step by step of how we have done it actually. So what we do is, we basically, as I told you, we are supposed to be pulling the Docker containers, okay, from the NGC site, right? So we have tried to download the PyTorch this thing, okay, and then we basically pulled the Docker container. So we are actually telling you step by step of how we did it, right? All of this is executed. So whatever we tried to do till now, we have actually tried to put it on the slide so that tomorrow when you want to do it, okay, you can actually see it automatically and do it step by step, right? So this is how, when you run it, you basically try to run that program, okay, then you load the pre-trained network, you get the image for production, then this is the transformed image, then you see the batch size, probability prediction for CPU, okay, and then you do it for GPU, the CPU benchmarking, the GPU benchmarking, and then TRT model benchmarking, okay, something like this.